Hi, and welcome to Dr. Vanderveen's AP Chemistry podcast. Tonight we're talking about hybridization. Now, the objectives for this podcast are to relate molecular geometry to hybridization and to do some practice problems. I do want to, before we jump into this, I do want to go over with you why we care. Why does this term hybridization come up? And for our purposes, we can think of it as a way to reconcile known geometries with the orbitals around the atom, and to make it all work. Because if you look at the orbitals, if you look at your s and your p orbitals, which are usually the orbitals that we're dealing with in bonding, going from these orbitals to something that is tetrahedral, or to go to something that is linear, or to go to a geometry that is trigonal planar, it doesn't work directly. So hybridization is our way of mathematically making the orbitals match up with the geometries that we know about. Focus, however, is going to be on what you really need to know. All right. So we'll talk a little bit about how this happens, but we'll emphasize what you need to know. So let's start with a linear geometry. Now, in order to get a linear geometry, you have two electron domains around the central atom. All right. And if your central atom has got s and p orbitals to play with, this doesn't give you linear when you try to bond with these guys. So what we're going to do is mathematically blend them together. This is called hybridization. We started with two orbitals, two atomic orbitals, and we're going to get two hybrid orbitals that belong to the whole molecule. All right. And now that we have these hybrid orbitals, we can see if this is our nucleus right here, and if we put them together and only look at the large lobes, we can see that we now have two orbitals that are 180 degrees away from each other. The long and the short of it is, if you have a linear geometry, if you have something with two electron domains around your central atom, you will have what is called sp hybridization. Sp because it comes from an s orbital with a p orbital to make two new hybrid orbitals. The next thing I want to talk about is trigonal planar geometry. Right now, in order to get a trigonal planar geometry, 120 degree bond angles. Again, if you look at the s and p orbitals, this doesn't happen obviously, all right? But when you have three electron domains around the central atom, what we are going to do is take an s orbital and two p orbitals, so three atomic orbitals, and we are going to make three hybrid orbitals. And we're going to do this by this magic hybridization process that we're not going to really explain at all. And these hybrid orbitals are called sp2 hybrids because they're made from an s orbital and two p orbitals. So they're called sp2 orbitals. And you'll notice when you look at the large lobes of all three together, look, you have that trigonal planar geometry. You have that 120 degree bond angle. And so the take-home message here, guys, that if you have a trigonal planar geometry, if you have three electron domains, then you have sp2 hybridization of your central atom. Next is tetrahedral geometries. Right? If you have 109.5 degree bond angles and four electron domains around your central atom, and we're going to call this sp3 hybridization. I don't feel comfortable just telling you that. Let's talk a little bit about how we get there. If we look at, say, a carbon atom with its four valence electrons, those valence electrons go in the 2s and 2p atomic orbitals. But if you look at your geometries, this does not give you a tetrahedral geometry, all right, this here. So what we're going to do, one way to think about what we need to do is we can take one of our electrons in the 2s orbital and pop it up to the 2p orbital. This is called promoting it, which now gives us one electron in each orbital. We still don't have 4 orbitals 109.5 degrees apart, as we know, for example, that methane has. So what we're going to do is take these orbitals and mathematically blend them. Again, we said this is called hybridization. It's a big, giant math thing. And we're going to make 4 hybrid orbitals from those s and p orbitals. And we're going to call them sp3 orbitals because they were made from an s orbital and 3 p orbitals. Let's show this a little bit more. If we start with this, okay, so we still have our carbon with our 4 valence electrons. If we take these 4 atomic orbitals, all right, a spherical s orbital and 3 dumbbell-shaped p orbitals, we can mathematically blend them together to form 4 hybrid orbitals. Which just happen to have the exact geometry we want. All right? And since these hybrid orbitals were made from an s and 3 p orbitals, we call them sp3 orbitals. Right. Now, if we have a trigonal bipyramidal geometry with 5 electron domains, the hybridization is believed to involve d orbitals. We call these sp3d orbitals. So similarly, all right, we can have, instead of starting this electron configuration off, we're going to take one of these s electrons and promote it to a d orbital, which gives us this. That's not going to give us what we want, so we're going to hybridize them and end up with 5 identical orbitals. Now, I do want to point out there are some unused orbitals. All right, which some d orbitals which did not get used, and this happens with some p orbitals in sp and sp2 hybridization as well, I should mention. All right, but now we have 5 sp3d orbitals that we can use for our geometry to have the right bond angles and the right orientation. Finally, we have octahedral geometry, where there are 6 electron domains around the central atom. And again, to explain all this, we need to invoke those d orbitals. So we're going to take an s orbital and 3 p orbitals and 2 d orbitals. And we're going to blend them all together. I'll take all of those 6 atomic orbitals and make 6 identical sp3d2 hybrid orbitals. Perhaps you've noticed the pattern. If there are 6 electron domains, I have to blend 6 orbitals to make the hybrids. All right, if I had 5 electron domains, I blended 5 orbitals. All right, so let's summarize this. A number of electron domains, 2, 3, 4, 5, and 6. Well, if I have 2 electron domains, the geometry is linear. I know my bond angles are 180 degrees, and my hybridization is sp. If I have 3 electron domains, that is a trigonal planar geometry. My bond angles are 120 degrees, and I have sp2 hybridization. If I have 4 electron domains around my central atom, this is a tetrahedral geometry, where my bond angles are 109.5 degrees, assuming I don't have any distortions due to lone pairs. My hybridization is sp3. If I have 5 electron domains, we're talking about trigonal bipyramidal geometry. And the bond angles are either 90 degrees or 120 degrees, depending on the location in the molecule. My hybridization is sp3d. And if I have 6 electron domains, my geometry is octahedral. My bond angles are all 90 degrees, and my hybridization is sp3d2. So the truth is, if you know this table, you know there, this is enough to get you through the test questions you should expect to see I always like to explain how we got there, all right? But long and the short of it is this table is really the summary of everything you need to know.